Welcome to our first step towards what typically is the capstone of calculus, namely vector calculus, the calculus of vector fields. Well, basically, if you've ever asked yourself the question, what makes strings attached to a Van de Graaff generator stand up? And basically, this is a Van de Graaff generator. We've attached some strings to it, and if you run that Van de Graaff generator, you see something like this. These strings stand up. And if you've ever asked yourself what makes iron shavings align themselves around a magnet, if you take a permanent magnet and you sprinkle iron shavings around it, you get a picture like that, and that is a picture that I've taken myself. Well, the answer, of course, is vector fields do. Namely, these iron shavings align themselves with the magnetic field of the permanent magnet, and these strings that are attached to a Van de Graaff generator, when the generator runs, these strings are getting charged and then they align themselves with the field lines of the electric field around the Van de Graaff generator. They're a little curved here because these strings have mass, and so they're also attracted by the gravitational field of the Earth. Okay, so what we will do is we will discuss the mathematical definition of vector fields. We will discuss standard representations of vector fields, and we will discuss the vector fields that we most commonly work with, and that's what we can see already here in the headings. We're going to talk about central force fields, we're going to talk about vortices, we're going to talk about gradient fields, and we're going to talk about flows. The interesting thing is there that for the dynamic picture that we have of vector fields, flows are the best visualization, but flows are also the most complicated entities to model mathematically, which is why we typically stay with vector fields that, even though we think of them in terms of flows and of fluxes, such as electric fields and magnetic fields, these fields actually don't really transport any mass. Okay, so the mathematical definition is that if we have a region D in n-dimensional space Rn, then a vector field on that region is a function f that assigns to each point x1 through xn in D an n-dimensional vector f of x1 through xn. So that is just another function, essentially. We've seen this often enough. This is basically verbatim the definition of a function of one variable, except that now we're mapping n variables to an n-dimensional vector, right? The visualization of these things, the graphs of these vector fields, are, well, technically simple, but certainly laborious to draw, and that is basically at every point in space, you can just go ahead and draw the vector, and if you're looking at a two-dimensional vector field, then you get a nice, easy to visualize two-dimensional picture like we have here. So, for example, the value of this vector field at this point is exactly this vector, and we can see that this is something like a vortex, right? Okay, so in 2 dimensions, a vector field then usually in calculus texts has components p and q. At least that's what I have seen in many calculus texts that I have looked at. In 3 dimensions, a 3-dimensional vector field f of x, y, z usually has components p, q, and r. Now, there is no law that says that these components have to be called p, q, and r, but that's what you typically see in calculus books. And we're already moving on. We want to now represent vector fields, and we're going to talk about the same vector field here in 3 different ways. Namely, we're going to talk about the electric field generated by a negative point charge, negative q, at the origin. That field has magnitude E of r being q over 4 pi epsilon 0 r squared, where r is the distance from the origin, and the field vector points towards the origin. This is a description that you typically see in physics because it is very sensible for a field that has a certain symmetry, such as the symmetry that all the field vectors point towards the point charge, which is at the origin, so all the vectors point towards the origin. For such fields, it is very sensible to separately discuss the magnitude of the field, which is given by the electrostatic force, Q over 4 pi epsilon 0 r squared, that's Coulomb's law, and then separately talk about the direction of the vectors. And then, of course, this field sort of looks like this, right? All the vectors point towards the origin. The vectors get smaller as you get farther away from the origin, and they get larger, longer, stronger as we get towards the origin. And at the origin itself, the field is undefined because we cannot divide by 0. Now, another way to describe that same electric field generated by a negative point charge, negative q at the origin, is by saying that the field is actually vector E of vector r being negative q over 4 pi epsilon 0 r squared. So again, the magnitude here without the negative sign, so just the magnitude. And then we multiply that by the position vector of the point divided by the length of the position vector. So this is just a unit vector that points away from the origin, and this negative sign makes it a unit vector that points towards the origin. So again, we have magnitude times direction separate. It's just that this time we don't explicitly verbally separate it. This time we actually have it all included in one formula, where of course lowercase r is just the magnitude or norm of the position vector r itself. This description is also often used in physics when you want to have this as a handy formula that doesn't include details on the components. Well, finally, this electric field generated by a negative point charge, negative q at the origin, can also be described as given by E of r being negative q over 4 pi epsilon 0 x squared plus y squared plus z squared to the 3 halves times x, y, z. And then, well, let's talk about that first. That's the same field as over here because we still have the negative sign. We have the q over 4 pi epsilon 0. Wants to pick up the r squared here, but we've got the q and the 4 pi epsilon 0 here. And then in this formula, we've got r squared times r in the denominator, which is r cubed. Well, r is the square root of x squared plus y squared plus z squared, so that's x squared plus y squared plus z squared to the 1 half cubed, and that's x squared plus y squared plus z squared to the 3 halves. And then this r here is the vector x, y, z, as we can see here. So it is again encoding the same field, and if we are interested in the components, and we will be when we'll be talking about gradient fields, when we're going to show that this thing is a gradient field, then we will be interested in the components. And of course, finally, it is also possible to pull all the constants out front into the components and to write this as negative qx over 4 pi epsilon 0 x squared plus y squared plus z squared to the 3 halves, and the same thing with negative qy divided by the same denominator, and negative qz divided by the same denominator. So the description of a vector field will depend on the context, and we need to be able to translate back and forth between these formulas, and certainly translating from here to here to here isn't too bad. The more complicated situation is sometimes we may also have a vector field where we have to translate from something like this to something like that, or something like that, because we want to attach meaning to what the symbols tell us. But when we get there, we will do so. Okay, so each of these representations basically is useful. I've already indicated number 1 is often used in physics books when you are looking at more of a descriptive way to separate the magnitude from the directions of the vectors, whereas the last one, of course, is much more useful when you have to do computations with the components, because it gives you the components explicitly. And so each of them is useful because each communicates the same thing in ways that are more or less appropriate in certain contexts, such as verbally describing a field versus actually doing computations with it. As a note, fields like the field of a point charge are called central vector fields or central force fields in physics, because typically there are forces such as the electrostatic force certainly associated with these fields. images of these fields may need to be enhanced, because if we're looking at the field f of r being negative 1 over r squared r over r, we just visualized that as this field because we wanted to see some vectors. However, if we actually plot this thing to scale, it actually looks like this. And that's where we can see, yes, it is the same field. It's not quite as pretty anymore, and certainly, I mean, here we don't even see that this is a vector anymore, and that's because this field just declines so quickly. It declines with 1 over the square of the distance from the origin, that out here we don't see the vectors anymore very much, and often a field of a point charge is getting really hard to measure if you're quite far away from where the point charge is at. So every so often, images will not exactly represent what the vector field is, but that is okay, because what we want to use these images for is visualization. Okay, let's talk about another very common type of field, and that's a vortex. And if we want to sketch the vector field f of r equals 1 over x squared plus y squared times the vector negative yx, well, what is that? The length of the vectors is that you just take, well, this 1 over x squared plus y squared is just a factor that factors out of the magnitude also, and the magnitude of this vector here is the square root of the x component squared plus the y component squared, so it's the square root of negative y quantity squared plus x squared, and if you work that out, that's 1 over x squared plus y squared, which is 1 over r, 1 over the distance from the origin. And then how do you visualize this thing? Well, one way to look at this thing is that this thing is perpendicular to a vector that points straight away from the origin, which means that this will be something that is a vortex that either spins clockwise or counterclockwise, and basically it looks like it spins counterclockwise, and here's the image of the whole thing. Because what we have here is all these vectors are perpendicular to vectors that come straight off the origin, and then if we're looking in the first quadrant, well, y is positive and we're going in the negative x direction, x is positive, we're going in the positive y direction, and if you look at that in all 4 quadrants, you really see that the directions of these vectors need to be like this. So this is something that takes a while to figure out, and certainly just knowing that these things are perpendicular to vectors that come off the origin don't give us the whole picture. You have to plot a couple of these things, but ultimately what you get as you plot enough of these things is a vortex that spins counterclockwise. Interestingly enough, this is actually not necessarily a vortex in a flow. We're also going to talk about that. This is like the magnetic field that surrounds an upward current in a vertical wire through the center, because the magnetic field in an upward current in a vertical wire through the center is something that is circular around the wire, and its direction is determined by a right-hand rule, where if the current goes upward, then the right-hand rule dictates that it spins counterclockwise. We're going to see that right-hand rule in a future panel, actually. And the magnetic field declines with the distance from the center of the wire, so it declines with 1 over r, not with 1 over r squared like the magnetic field. So this really is an exact description of such a vector field. And the right-hand rule for magnetic fields around current basically is that if the current is in the direction of your thumb, then the natural curvature of your right hand describes the direction of this circular magnetic field that goes around that current. And so this right-hand rule will also be used for the orientation of the boundary of a surface, which is something that we at the latest will have to worry about when we talk about Stokes' theorem. Vortices, okay, so this vector field, even though it looks like a vortex, and when I think of vortex, I always think of flows, this vector field is actually not a model for vortices in fluids. It looks like this, whereas vortices in fluids, such as this one, and this is of course the most destructive vortex in fluids that I think we can observe on planet Earth. This is a hurricane. This particular one is the Hurricane Andrew. These things certainly don't do good things when they hit populated areas, but at the same time they are examples that we want to model so that maybe ultimately there will be something along the lines of hurricane prevention, hurricane forecasting already, because of models that we have, has gotten very, very good actually, and allows us to warn people in the path of a hurricane to at least take measures. And so that is a vortex. This is something where the winds certainly are circular. The image is from the National Oceanic and Atmospheric Administration, which has a nice fair use policy that allows the use of these images. And vortices in fluids actually look more like this, and I have to be really careful near the center. We have to be very careful to talk about just about this near the center. And basically there is data where people have actually flown airplanes across the vortex of a hurricane, and near the eye of the storm, the wind velocity really increases linearly with the distance from the center of the storm. That is in some ways then a reason why these hurricane force winds are so strong, because if, as is also observed in the eye of the storm, things are calm, but the wind velocity increases linearly with the distance of the center, from the center, you can imagine that 50 miles from the center, there is a lot of very, very strong winds. Of course, once you get far enough away from the center, thank goodness, the winds taper off again, because a storm, a superstorm, as often is talked about in science fiction novels, where this linear increase of the wind velocity doesn't taper off until it's several hundred miles away from the center, that would be severely catastrophic, because these winds would just be close to unimaginable, I think. So near the center of these vortices in fluids are often modeled rather nicely, actually, by a vector field that is this negative y over x, a negative y in the x component, x in the y component, which has a magnitude that increases linearly with the distance from the center. Of course, once you're then past that region, you have to put something on there that makes the wind velocity decline for the model. And linear increase also means that typically there is some kind of constant of proportionality up front here. Okay, so let's now talk about gradient fields. For a multivariable function f of x1 through xn, where x1 and xn are interpreted as space variables, the gradient vector field of f is given by gradient of f, or nabla f of x1 through xn, and it's simply that you take the nabla operator, partial with respect to x1, partial with respect to x2, all the way through partial with respect to xn of f, and that's just partial f with respect to x1, partial f with respect to x2, all the way through partial f with respect to xn. So that basically says that this gradient operator that we already know takes a function of several variables and turns it into a gradient field. Great. The interesting thing is that gradient fields have great physical relevance, so we're going to explore the operator as well as one physical context, namely the gradient field that is the electrostatic field, in more detail. So, as an example, compute the gradient field of the function f of xy being x squared minus y cubed. Well, that's just a straight computation. Nothing to it, right? We just take nabla f of xy, which is just a nabla operator, scalar multiplied with the scalar f. That gives us df partial f with respect to x and partial f with respect to y, which is the partial of with respect to x of x squared minus y cubed, and the partial with respect to y of x squared minus y cubed, which gives us 2x and negative 3y squared right here, and that's it. So in terms of visualization, the function x squared minus y cubed, if we're looking at a contour plot, that looks like this. This thing, if we're subtracting y cubed, of course, it's going to get large for negative y values, and it's going to get really small for large positive y values, and the x squared gives a little bit of a twist in the x direction to the whole thing. And if I superimpose the gradient field on that, then we can see that, of course, near the origin, x and y are small, so the gradients are small, and as we get farther away from the origin, the gradients get longer. And these gradients are always, as we have also talked about, they are perpendicular to the level curves in this contour plot. So this is the kind of thing, if this was, say, a heat, if this was a heat diagram, remember the gradient points in the direction of steepest ascent. If this was a heat diagram, then of course thermal energy would flow in the opposite direction of the gradient here. Okay, so this certainly also tells us again that the gradient then has physical meaning, in the sense that if we're looking at heat or pressure, okay, we would have to reverse all the arrows, but it would give us the flow direction of air if this was a pressure map, for example. Okay, so I'm sorry, I'm jumping between a variety of interpretations here, and basically what you want to have is you want to always interpret the vector field in a certain way, and as I said, flow is one of the natural interpretations. We just have to be careful that we make sure we've got our negative signs right. Okay, as a theorem, the electric field generated by a point charge really is a gradient field. And the same is true for the gravitational field of a point mass. And that is because if we disregard constants, which we can for this analysis, so the q over 4 pi epsilon 0 can be taken out, or the g times the masses of the two objects can be taken out, then both fields are really just of the form field being 1 over x squared plus y squared plus z squared to the 3/2, 1 over the distance from the origin cubed, times x, y, z, which is a vector that points straight away from the origin. And if we now recall that the derivative of t to the negative 1/2 is negative 1/2 to the times t to the negative 3/2, then we notice that really there is a good chance that the function 1 over r, 1 over square root x squared plus y squared plus z squared, would be so that its gradient is this function here. And well, if we take the partial derivative of 1 over square root x squared plus y squared plus z squared with respect to x, what do we get? We get the partial with respect to x of x squared plus y squared plus z squared to the negative 1/2, which will give us negative 1/2 times what's inside to the negative 3/2 times the derivative of the inside, so it gives us negative 1/2 times the inside to the negative 3/2 times the x partial derivative of what's inside, which is 2x. And if we simplify that, we get negative x over x squared plus y squared plus z squared to the 3/2. And of course, a similar computation for y and z will show that the gradient of 1 over square root x squared plus y squared plus z squared is negative 1 over x squared plus y squared plus z squared to the 3/2 times the vector x, y, z. And that, of course, shows that the field on the previous panel is a gradient field, because this negative sign can simply be moved over. So the gradient of negative 1 over r is the field that we had on the previous panel, and that shows that the crucial part, the part that that actually depends on position, the part that comes after the constant, that part is really the gradient of another function. So that is certainly one of the reasons then why physicists are so interested in gradient fields, because electricity as well as gravity are very important phenomena, and the fact that those things are gradient fields then really helps us with their description. Another question that you may ask yourself is, how do you find the gradient of a vector field that is given to you? Well, we've just seen that I've done a little bit of neat pattern recognition that basically also comes from the fact that people just know that the gradient of 1 over r is negative r over r cubed. That isn't necessarily something that I would want people to memorize, but it is something that ultimately you can't help but remember. But so if you ask yourself, how do you find a potential function whose gradient is a given vector field? Well, this example will show us that in a little bit more detail. So if possible, we want to find a function f so that the gradient of f is 2y cubed and 6xy squared plus 2 in the x and y components respectively. Well, basically, if this is the x component of a gradient field, then this is the x derivative of f, and so we could just take the x integral of this function, and what we get is 2xy cubed plus a constant that could depend on y. So plus a function that depends on y, because if I take the partial derivative of this right-hand side with respect to x, well, then the derivative of a c of y would be 0, and I would still end up here with 2y cubed. Well, if this is the y component of a gradient field, then this would have to be the y partial derivative of f, and so in order to recover something that ought to look like f, we would want to integrate this y component with respect to y. And what we get is, well, the antiderivative of 6y squared is 2y cubed, and then the x stays with us, so we get 2xy cubed. The antiderivative of 2 with respect to y is 2y, and then we have a c of x here, because again, if I were to take the y partial derivative of this right-hand side, the derivative of anything that only depends on x would be 0. And we can see that as a double check, also the derivative of 2xy cubed with respect to y is 6xy squared, and the derivative of 2y with respect to y is 2. So that also works out. And so what is f now? Is it this one or is it this one? Well, actually, what you need to do is you need to overlap things, and stuff that occurs in both isn't being added. Stuff that occurs in both will also occur in the potential function, as this thing then is also often called. I think I may be losing a negative sign here in the language, but we'll see that on a later panel. Either way, in this potential function or not, anything that occurs in both of these antiderivatives also has to occur in the potential function. Anything that occurs only in one, but only depends on the... okay, so anything that occurs in both. Well, so the 2y doesn't explicitly occur here, but it is something that only depends on y. So that also occurs in both, so the 2y is okay. C of x, well, c of x doesn't occur up here, so that's something we have to drop. And what we could, of course, have ultimately is we could have a plus c. And if you look at this function, well, if you take the x partial derivative and if you take the y partial derivative, you realize that the x partial derivative is what we want to have here, and the y partial derivative is what we want to have here. So this function actually is so that gradient of f is this vector field. So in terms of how do I find a function whose gradient is a given vector field, I take these integrals and I have to do some pattern matching after that. In terms of visualizing it, here is the field and here is the function. And I have to apologize here, the picture scale is a bit problematic. The gradient, of course, is supposed to always be perpendicular to the level curves. That isn't always happening in this picture because I spent about, I think, 1, maybe 2 hours trying to take two different ways of rendering different objects that aren't entirely compatible to make this work out, until I had something where I realized, look, I can do better things for my students, I can do better things for you than continue to mess with this picture. And so, yeah, it's not quite right, but again, it gives the impression that we want to have, that f is the function which gives us certain heights and the gradient is perpendicular to the level curves. Alright, we move on. And another example, if possible, let's see if we can find a function f whose gradient is this vortex negative y x. Well, if I take the integral of negative y with respect to x, I get negative xy, and I could potentially have something added that only depends on y. If I take the integral of the y component with respect to dy, I get integral x dy, which is xy plus something that could potentially depend on x. And the problem now is, even though I have xy in both of these integrals, I have negative xy in the first one, and I have xy in the second one. So actually, this is not the same function occurring twice. These are two different functions. And so because there is no way to combine these two antiderivatives into one function that works out, this field is not a gradient field. Now that is something that depends on our acceptance that this pattern matching works out, but basically, if there was a function whose gradient is this vector field, it would have to contain negative xy and it would have to contain xy. Well, if it contains both of them, well, then it would be 0, or basically if it contains only one of them, then it will not contain the other one, because we always have a problem with the negative sign. So that means that vortices are not gradient fields, and that is something that we will also talk about from a physical point of view, because basically if you travel around a vortex, you can pick up energy from the vortex, and that is something that does not happen in a gradient field. Okay, and that is something we will see in the presentation after the next one, because we will need the fundamental theorem for line integrals for that. All right, proposition. If you didn't like this argument, there is another nice result that says if I have a vector field with continuous second partial derivatives, where the components now are just f1 through fn, and then, well, if that vector field is a gradient field, then we must have, for all indices I not equal j, that the partial of the ith component of the vector field with respect to the jth input variable is the partial of the jth component of the vector field with respect to the ith input variable. And why is that so? Well, that is because if f is a gradient field, gradient lowercase f, then for all indices I not equal to j, we have that the partial of the ith component of the vector field with respect to xj is the partial with respect to xj of the partial with respect to xi of f. And we know that if we have continuous second partial derivatives, that then we can interchange the order of differentiation. So this is the partial with respect to I of the partial with respect to the jth direction of f, partial with respect to xi, of the partial with respect to xj of f. And that is nothing but the partial with respect to xj of fj. And that's exactly what we wanted to prove, because now we have on the left side this term here, and on the right side this term here. So in some ways, as we're going through the concepts of multivariable calculus, we're also building some proof writing capabilities here, because that's a proof that we ought to be able to understand, right? Okay, so now as an example, let's look at this function f. Let's look at this vortex field one more time, and let's now prove that there is no function f such that gradient of f is negative y in the x component and x in the y component. Well, if I take the y partial of the x component, I get derivative with respect to y of negative y, which is negative 1. And that's not equal to 1, which would be the x partial derivative of the y component. And, well, because by the previous proposition we know that if this was a gradient field, these two would have to be equal. They're not. Therefore, this field is not a gradient field. Okay, final example here. Oh, yeah, now just, I guess I should have said definition here, but let's just move on now. It's also an example, if you will. The vector field negative gradient of f is also called the potential field of the potential function f in physics, and that is because at every point the potential field points in the direction of steepest descent, not ascent, for the potential function f. And that is because physically, potential fields point in the direction in which an object that is drawn from higher to lower potential would travel. And of course, in physics, objects typically travel from higher potential to lower potential. If you're looking at the right object, such as a mass in a gravitational field, potential is determined by how high you are, how far enough away you are from the mass, and so you would travel in the downward direction because you're gaining potential energy as you're going up a mountain, for example, and then water flows in the direction of the gradient, serpentines down the mountain if the mountain has some a riverbed or something like that. Otherwise, it flows straight down. Or also positive charges, where typically the farther away you are from negative charges in an electric field, the higher your potential is supposed to be. And then I put positive charges, of course, attracted towards negative charges. All right, so let's talk about adding vector fields. That is something that is not terribly hard. It's just an important visualization, and that is if we want to sketch the vector field f of r being negative 1 over r squared r over r plus 1 over r minus 2, 0 squared r minus 2, 0 divided by r minus 2, 0 magnitude. Well, that is basically something that looks like the electric field of a negative point charge at the origin plus a positive point charge at the point 2, 0. And that's something that I would want us to certainly work out with a computer. And what we can see is that we have this central force field here of this negative point charge where the arrows are pointing towards the center, and this central force field here of the point charge where the arrows are pointing away from the origin, and then they add to each other to something that looks sort of like things would flow in these directions from the positive charge to the negative charge. And the picture certainly is enhanced. I made the arrows longer than they actually are if we were to draw this to scale, because otherwise we would get one of those pictures, as we have seen earlier, that just has a bunch of dots. Okay, so this is something where ultimately you really want to use software. The main thing is we want to accept that we can add vector fields, which is, of course, from a mathematical point of view, not terribly hard at all. You just add the vectors, right? But basically, it is physically very important, and so the superposition of vector fields, or the superposition principle of vector fields, really is that if you have two compatible vector fields, say electric fields generated by two separate charges, then their effects really are added like vectors in mathematics. That is something that actually has to be verified experimentally, because if nature didn't act that way, then we would need a different tool to describe these fields. Thankfully, nature does act that way. These effects really add to each other, and that is why vector fields in the mathematical definition, which we have introduced, are really a good tool to describe physics. Otherwise, all this stuff that I'm saying here about physics, I couldn't say because it wouldn't be the correct tool, right? Okay, so now, definition. Of course, in physics, people also draw the flow lines of a vector field. So if f is a vector field, then the vector valued function c is a flow line or a streamline of the vector field f, if and only if, for all indices t, we have that the velocity, or the tangent vector, if you will, the velocity of this vector valued function is parallel to the vector f of c of t. I just say parallel because the velocity may have a bigger magnitude than this vector field. It may not be compatible at all, but we want to have parallelity, because basically that means that at every point of the curve traced by c, the vector field is tangential to the curve. And of course you have seen these flow lines before in standard pictures, such as, for example, the image of a permanent magnet, where we know that magnetic field lines go from the magnetic north pole to the magnetic south pole, and then technically actually inside the magnet the magnetic field lines close up again. Magnetic field lines are always closed, and so they just work in inside and outside on the top and bottom in exactly this fashion as indicated in this picture. So the flow lines or streamlines of a vector field are what you have also seen in the picture of the iron shavings in the field of a permanent magnet that I showed you in the introduction, right? Flow lines, of course, can also be used to describe electric fields, and that's probably also a picture that you have seen in physics. It's the flow lines of that field that we have just talked about when we were adding vector fields, and that is just flow lines that are tangential, so that the vector field is tangential to these lines. It sort of shows that the electric field lines just go from the positive charge to the negative charge, and they might get really, really huge, but ultimately they still link up going to the negative charge. Okay, this one I guess would go across the point at infinity, if you will. That's where things become really, really abstract and mathematical. The interesting thing, however, is that, remember, as long as we don't put anything in there, the electric field, the electrostatic field, is, as the name says, static. It doesn't transport anything. So that's what we call these things field lines or streamlines. There's nothing really literally flowing. And well, once we put a mass in here, it's not the field that flows. Once we put a charge in here, it's not the field that flows. It's the charge that moves. Similarly, the magnetic field, of course, really doesn't move anything. It just sits there, and only if you put another magnetic object in here may there be some kind of motion. So these fields, in vacuum, they exist. They don't transport anything. When we talk about flows, we're really much more prone to think of flows as velocities of, say, a fluid flow. So flow fields can also give the velocity as a function of space. And so then, for example, the laminar flow in a water pipe, let's say, would be that in a fluid flow, everything flows at the same speed in the same direction. Of course, that is then not realistic in a water pipe. The water molecules that are closer to the boundaries of the pipe are slower because of adhesion than the molecules that are in the center of a pipe. So a literal fluid flow of water molecules in a water pipe is probably better described by a flow field where the flow velocity is largest in the center and tapers off towards the boundary of the fluid flow. And then, of course, you can also have flows where you can see where the flow compresses and decompresses, where you've got something really fast coming in this region. It's decompressing because it's flowing very slowly here, and then here it's compressing here, and then here it is decompressing again, because here the flow velocity goes from small to larger. This is the kind of thing that you could think of as a traffic flow, even though if every one of these arrows was a vehicle, then this would really be a super highway with, what is it, 9 lanes here. I'm not sure if that would even be, if that even exists anywhere, and if it would be sensible to construct. But certainly then, if you talk about velocity, you can also technically talk about things like traffic flow and use ultimately even models that are designed for continuous scenarios in order to describe discrete phenomena such as traffic. Okay, and so finally, David Austin's applet flows of vector fields, which I can use with his permission. I emailed him and he was nice enough to let me do that, can also help visualize flows. If we're looking at these things, this applet just has a variety of vector fields. And so, for example, here we've got a very simple vector field, which is just 1, 0, so everything just goes in the x direction at uniform speed 1. And in this applet, you can actually put something into the flow and look at how the mass, the sample particles, if you will, that you put into that flow, how those things behave. And so if you've got a nice uniform flow, then if I were to put dye into this flow like this, then this patch of dye would just move like that. Well, of course, that can change if you've got a flow that goes around the origin. Well, then the patch of dye will work a little bit differently. But if this is one of those flows that is such as, for example, around or near the center of a hurricane, then again, there is no distortion of this patch of dye, because the larger velocity on the outside makes sure that all the particles keep up with each other. Well, if we look at this then from the point of view of having a field that is more like the field that is around a vertical wire, where the flow velocity is faster at the center and slower around the outside, such as, for example, also is the case in that vortex that you have when you empty a bathtub. At least it seems to me that way. Well, then if you put some dye into that, you realize that that dye is being pulled apart, because certainly farther away from the vortex as you're draining a tub, not much is happening, whereas in the center stuff is draining more and more rapidly. And that's where this dye patch then, of course, gets distorted very much. So if you look at this farther out, that's where the distortion isn't too bad, but of course it also is visible there because, again, particles near the center are moving faster than particles that are farther away from the center. So this is an applet that, if you want to, you can certainly play with a little bit more. It certainly is rather neat to then also see how a repelling field would distort something, because a repelling field would ultimately just really enlarge things. It would decompress things quite a bit. This is the kind of thing that happens in unfortunate events such as explosions, right? We've got rapid decompression in all directions, which basically means that there isn't more air in the explosion. It's just that that air is being pushed outward very, very rapidly. All right. Well, I hope you enjoyed this presentation, because really the stuff that we can assess here isn't much at this stage. You'll be drawing a couple of vector fields, you'll be computing some gradients. Well, big deal, you know how to do that already. You'll have to probably find some potential functions. That's a little bit more complicated, but really the main seed that we have to sow here in this presentation is the fact that these vector fields describe a multitude of highly important phenomena in reality. They are an important tool, and the drawback that we have right now in such a class such as this one, where we're just getting started, is that the models themselves are quite complicated. And so the direction that I have taken here is I have not described the stuff that we can describe, or that we can just easily compute. I've really made a point of showing you reality. Vortices, magnets, electric charges, actual flow fields. That's the kind of stuff that you will be facing in applications, and the more you can make a connection between these applications and the mathematical description through vector fields, the better these applications will go for you. All right, sermon ends. I hope I haven't hicked up too much in some of the descriptions where I was where my enthusiasm got the better of me. Have fun with some homework. We're going to start computing line integrals in the next presentation.